Laikas, buenos días, podemos empezar. Ahora veremos un vídeo sobre el tema Sistemas globales de navegación por satélite. Basics and how to become an expert in this area en inglés. Después de ver el vídeo, ustedes pueden hacer preguntas al representante de la Universidad Aeroespacial de Samara, Kudravtsev Ilya Alexeyevich, investigador senior de la universidad, profesor del Departamento de Investigación Especial. Gracias, colegas. Empezamos.
Buenos días amigos. Hoy quisiera os contar de navegación de satélite, pero no estoy seguro de mi castellano, por eso prefiero inglés. You can see the topic of my lecture, and GNSS stands for Global Navigation Satellite System. Mariners are always interested in two questions: where we are and how to rule the ship to get to the destination. Maybe the navigation is one of the most ancient skills of the humanity, and the navigation is very important when your ship is far from shore, when you do not see the shore. It is challenging. Our Earth is a globe, and it is more or less essential that the coordinates could be described with meridians and parallels. So the names of these parallels and meridians are known from very ancient times, and we can describe our position using these coordinates. Of course, traveling with the globe is not that good. The globe could be quite big, and we rather prefer something like a map. You can see this scientist Mercator, and he is the person whom we owe by these maps. Maps were not maybe perfect, but at that time, many years ago, it was a great step forward. So having a map, you can understand where you are, and you can plan where to go. Having a map, you can easily plan your trip. You can just connect 2 points using a ruler, and then all what you need is just traveling along this line. This what we call loxodrome. The main idea is to keep the angle between meridian and your course more or less constant, and then you at the end get to the destination. However, when you far from your destination, it is not the best idea. In this case, we use orthodrome. So if you maybe travel to Europe, you can see that orthodrome in action. This orthodrome can save you a lot of time and a lot of fuel. So loxodrome and orthodrome are main ways of traveling, and orthodrome is relatively new, using when you travel for a long distance. How to determine your latitude. Actually, latitude could be measured as an angle between the horizon and the polar star. polar star, you know, is a star positioned almost uh, at the almost exactly at the north of our planet. So what you need is to measure the angle between horizon and polar star. It is easy to say, but try to do it on the deck of a ship with pitch and roll, so the accuracy is not that good. You can see a more sophisticated tool called sextant. Sextant is a tool used before we introduced satellite navigation. So mariners last 2 centuries at least used this sextant, and sextant allows us to determine the latitude quite precisely. You can see here accuracy here, and now I am sure that captains and navigators still have this tool at their box, because who knows, maybe some days satellite navigation will not be operable. Then sextant will work. Longitude. Longitude is about the time. By the way, you can see here very interesting person, Gemma Frisius. Gemma Frisius was an outstanding scientist of its time. Actually, he invented what we call triangulation, and we use this triangulation till this time. He offered also an idea that the longitude can be determined as a time difference between local time and the time of Greenwich. So the idea is, if you know these two times, the difference is longitude. Fine, but at that period we have not possession. We have no precise clocks. That was a problem. But Gamma-Frisius is great nevertheless. He is, by the way, the teacher of Mercator, and he also made some good modifications of this ancient um, latitude determination. He invented what we call astrolabe, so his contribution is really great. How to measure the time? Actually, time measurement is a problem. It was a problem until maybe 18th century. The most popular was solar clock. Of course, you can see that it could not be very precise. Knowing some astronomy, you can improve these measurements, but again, it is not that good. Actually, the method invented by Gemma-Frisius was not practical, could not be practical before we have poor clock. Actually, Mr. Harrison invented his chronometer, marine chronometer, in 18th century. If you are interested, this story, which is just mentioned here, is challenging. You can see the movie called Longitude. I'd recommend to do it. It is interesting, and how this Harrison and his son introduced the chronometer is very interesting. You can imagine the complicated mechanism using this picture. Of course, at the moment our chronometers are much more better. You can see here this Swiss chronometer used for marine navigation. You can see how precise it is. And of course, this accuracy was not available 200 years ago. Now it is available. And the idea is very straightforward. You have a chronometer configured to show the time of Greenwich, and you should determine the local time using, for example, sextant. It could be done if you know some astronomy. And now you have full information about your position. How to know where to go? Position is fine, but the course is a question. The very ancient instrument to do that, to know that, is compass. Compass, you know, shows us the direction to the north. Actually, compasses shows us the direction not to the North Pole, but to the northern magnetic pole. And magnetic North Pole and geographic North Pole are not the same. You can see here that the magnetic North Pole drifts, maybe not that quickly, but drifts, and the navigation using this magnetic compass is something vulnerable, especially if you are trying to travel somewhere at the north. But these magnetic compasses were used and still used for navigation. All the tools described above, I mean latitude, longitude compasses, are not accurate enough to be used when you are trying to get ashore. So, from the very ancient times, harbors were marked by lighthouses. Lighthouses are maybe the most romantic in the navigation. The idea is again very simple. It is just fire, light source, pointing the mariner where to go. Of course, the main limitation of this lighthouse is the distance. You cannot see that lighthouse far away. Maybe 10, 11, 15 kilometers. You can see here the formula of the visibility, but it is limited. It is limited also by the weather. And you cannot put lighthouses everywhere. After the radio was invented, the lighthouses were not maybe substituted by, but maybe modified using radio waves. Radio waves are available for very long distances, and using radio waves you can introduce hyperbolic navigation system. The idea of a hyperbolic navigation system is that if you have several stations, several transmitters transmitting radio waves synchronized between them, the ship may measure the phase difference between these radio waves received from different stations. And using this phase difference, you can define your, you can determine your position, for example, here and here, just on the cross point of these lines of equal phase. And it helped mariners to navigate. Actually, this is the most known instrument of radio navigation, hyperbolic navigation, called DECA. You can see that a lot of stations of DECA were built in Scandinavia, in Northern Europe. The navigation in these places, I mean Baltic Sea, Northern Sea, is not that easy. A lot of shallow places, a lot of fogs, a lot of problems. And this DECA helped mariners to travel there for a long time. Actually, DECA was abandoned maybe several years ago. It was operable for a long time from the end of the Second World War. Besides DECA, several several similar systems were proposed. You can see them here, you can compare them. However, GPS, Global Positioning System, outperforms all of them. Omega, transit, and so on, they are all in the past. However, this VORDME is still used for aviation. It is a system of positioning, of determining the direction for the aircraft, and it is still in use. The epoch of satellite navigation started in 1957, when the first satellite was launched. Actually, during the first launch, first flight, several attempts to use this satellite for navigation were undertaken. The idea is very simple. Satellite moving on a very well-known orbit is a beautiful lighthouse. It is seen and heard far away, and you can use this satellite to find a direction and to determine your position. And after that, several satellite positioning systems were invented. The principle is the same for all of them. You can see here that if you have three navigation satellites and the receiver here, and if you know the positions and the distance between the receiver to all the satellites, you can geometrically set the position of the receiver. That's all. Easy and straightforward. However, how to measure the distance between the receiver and the satellite is a different question. But you should know that no transmitters are used. All the navigators used in your smartphone and your car are just receivers. At the moment we have several global navigation satellite systems. They are GPS, GLONASS, Galileo and Beidou. GPS is the system of the United States, GLONASS Russian system, Galileo European, and Beidou is a Chinese system. They are global, I mean that they cover all the globe. We have also several regional systems in India, in Japan, and these systems are beyond our scope. Global navigation satellite systems comprises several segments. Actually, space segments, satellites, user segment, receivers on board your car, ship, aircraft and so on, and some control segment needed to control space segment. Actually, space segment comprises satellites on a specific orbits moving around the Earth, and these satellites transmit special navigation signal and navigation data. They inform receiver about their position. They inform about their accuracy and so on, so on, so on. How to make it precise depends on the control segment. Control segment is again beyond our scope, but we need them to maintain space segment. How we can measure the distance between a receiver to the satellite? Actually, you can see here a typical GNSS receiver. It is a radio receiver with radio frequency front end, analog to digital converter, and these two stages are specifically GNSS based. Acquisition is the process when the receiver tries to find out how many satellites are available, are visible, and what are the parameters of the signal. Then we can track these satellites with a lot of channels. Every channel tracks its own satellite. During this tracking, we can determine accurate distance, accurate time delay, what we call pseudo range, and also we can decode some navigation data transmitted by the satellite. All these distances measured by these receiver channels, tracking modules, are then passed to the computer microprocessor performing position calculation. One of the secrets of GNSS we'll see here the GPS technique is the signal transmitted by the satellite. The signal is specific. It is what we call CA code. It is the signal having several pulses transmitted during the epoch of 1 millisecond. Actually, 1023 chips inside this epoch. And this signal mixed with data bits with a throughput of 50 bits per second is mixed using exclusive OR, and then using modulator is transmitted from the satellite. These signals are transmitted from every GPS satellite. Every GPS satellite has its own CA code independent from other satellites. You can see here the generator producing this gold code. You can see that the generator is more or less the same, but we have a multiplexer which creates different points where we get the information from the generator G2, and the mixture of G1 and G2 signals provides output signal, again unique for every satellite. The main property of this gold code is the outstanding correlation characteristics. I mean that the autocorrelation function of the signal has very sharp and high peak. I mean that using these signals with this autocorrelation function can allow us to measure time shift between the same gold code but transmitted from different positions. Cross correlation between different signals is relatively low, so one satellite does not interfere another one. Thus, we have our own generator at the receiver, and we have the signal received from the satellite. Using some hardware and software, we can determine time shift. It is the time shift between the received signal and local signal. This time shift is the base for distance measurement. We call that pseudo range. It is the delay of the signal of the satellite. You can see here the more detailed block diagram of a GNSS receiver. It has some analog part. Then signal from the analog part is down converted to the baseband, and then here in this correlation module we perform acquisition. Acquisition, just recall, it's the process to find out whether the signal of a certain satellite is present and what is its delay and Doppler shift at the first approximation. Then it is maybe the same satellite, but the systems are a bit different to show you more details. This is the correlation module used for tracking. We have local version of our gold code, early, prompt, late, shifted for some interval, and this correlation module allows us to find accurate delay between our local generator and received signal. We have as many correlation modules as many satellites we use for our navigation. The signal from every satellite is then passed to processing unit to calculate position. Position determination is just a solution of the system shown here. This row 1, 2, 3 are pseudo ranges. So they are distances calculated using tracking modules as I described above. And then we know satellite positions and we want to calculate user position. Why do we need four equations when we use three-dimensional positioning? The fourth equation is needed because not uh, we have not an accurate clock at user receiver. Satellite receivers have very precise clock. They emit their signal simultaneously. But user clock is not precise. So we use another additional equation to compensate this delta, this time discrepancy between precise time and the clock time of the receiver. So all what we need is to solve this system. Typically, this is non-linear system, and to solve it with maybe additional equations, we use the trick called least mean square method. The solution obtained using this technique contains some errors. Some of them are, to say, physical. For example, ionospheric effects. Signal traveling from the navigation satellite. The orbit of the navigation satellite is about maybe 20,000 kilometers or so. The signal pierces ionosphere, and ionosphere is a place where total electron count concentration is present. So there are a lot of ions excited by the solar radiation. And in this media, the trajectory of a radio wave is complicated. You can this ionosphere can add some additional delay which will cause positioning error. This ionospheric error could be compensated by some techniques, and actually we also can use our GNSS receivers as a tool for searching for research of the ionosphere behavior. If you know the position of your GNSS receiver, you can measure intentionally these ionospheric delays, and using these delays you can say something about the physics of this ionosphere. I tell you this because it is an interesting example. We can use our GNSS receiver not only for positioning but for experiments, for physical research as well. Next problem is troposphere refraction. Troposphere is a lower layer of an atmosphere, and different temperature, different humidity, and so on could be the reason of refraction. So you can see that the trajectory of a radio wave is not very linear. We can compensate that using some models of the atmosphere, and again we can use our GPS receiver set at the point with well-known coordinates as a tool for some meteorological research, for example, to find out something about humidity, temperature of the troposphere, and so on. Next problem is a problem of reflected signals. In urban canyons where we live, if you live in a city, we have a lot of concrete, iron, and so on, and these materials can reflect signals. So the signal from the navigation satellite can get to your antenna, to your receiver, by different ways. For example, direct signal, this one, and this is reflected signal, and this signal is reflected twice. So all of these signals will have various delays, and when they are added at the antenna, they can affect the overall delay of the signal, so it could be the problem of positioning. To help the receiver to be more accurate, in positioning, some augmentation systems are used. Maybe the most popular are satellite-based augmentation systems. The idea is we have so-called reference station. Reference stations is positioned at the place with well-known coordinates. We have a GNSS receiver there. This GNSS receiver determines position using the signals of GNSS. And after doing this, we can find a correction. Correction, for example, due to the ionospheric or other kind of errors. Then we send this correction to master station and to antenna, transmit it to the another satellite of augmentation system, and the augmentation system will broadcast this information about correction to the Earth. So the user receiver gets the signal from the GNSS satellite, erroneous due to ionosphere, for example, and get correction from this augmentation system. Using these corrections, we can improve accuracy of our positioning. You understand that for aviation, for civil aviation and so on, it is very, very important. Another application of GNSS is what we call reflectometry. Reflectometry is a process of using reflected signals for our purposes. Just look at this picture. We have here a passive radar. This passive radar has a task of discovering and locating the ship. The signal from the satellite is getting to the ship, and then reflected version will come to passive radar. Passive radar will measure the difference between the signal received directly and reflected signal, and when okay, we know the distance between the ship. This radar is passive, it does not transmit anything, does not create any interference, but it knows well where the ship is now. So this technology called bistatic radars, passive radars using some signals like GNSS signal for positioning. Another option using reflectometry is some application in meteorology. I mean marine weather. This technology uses GNSS receiver, transmitter, broadcasting GNSS signals. These signals gets to the sea surface and are reflected and then received by a receiver, again satellite-based receiver on some low orbit. Just calculating the difference between direct signal and reflected signal, we can say something about the sea surface. If we have wind and waves, this sea surface scatter the signal by different ways, and the changes in this scattering could be registered and used for meteorology. This is not a very easy process, but it is used, and it is a challenging direction of our to say GNSS science. Now you know maybe some of the most interesting applications. Of course, we have a lot of different applications like time synchronization, precise agriculture, and many others where GNSS can be useful. I can say that GNSS technology is maybe one of the most complicated invented by the mankind. It comprises radio engineering, mathematics, simulation, programming, digital design, and many other things. So, in Samara National Research University, we have an educational program dedicated to this GNSS technology. Actually, what we propose is a master program, GNSS receivers, hardware and software. It is focused on creating GNSS receivers of different purpose for different applications. It is implemented within the area of radio engineering, and after graduating you will have a master degree. The goals of these programs you can see here. We are trying to provide the world-class level of education in the area of GNSS. I can say that not many proposes programs of this type. We are trying to provide comfortable conditions for research. I mean, you can participate in our research team, for example, in creating research satellites with support of GNSS. You can have a chance of study the courses internalized. I mean that some of the courses are taught by uh, the people, the lecturers from abroad, and you have a chance to uh, try intercultural interaction and try to participate in global cooperation. This is just an approximate list of the courses included into our program. You can see that some of the courses are very specific, dedicated to GNSS, and some of them are maybe more general. We understand that an engineer with a master degree of our university must be a good professional in in the area of GNSS, and also he maybe should have a chance of be maybe experienced researcher, experienced designer. He should be an expert in FPGA, in radio engineering, and other directions. So I mean that our program is created to be comprehensive. Of course, main focus is on the GNSS receivers. Actually, software-defined radio approach is used. Of course, you will have some basic knowledge in all relevant areas, and you will be able to use GNSS for various applications, and of course, create GNSS receiver by yourself. During the learning, we'll have some chances to create digital modules of the receiver, maybe some algorithms and programs. You will have a supporting course, Academic English. It is typically needed for the students for whom English is not their mother tongue, and you have some experience in studying with Russian-speaking students, and maybe some PhD students will be involved. So it is worth to try. You can see here that our teams, our students are really international. We have international students, we have international lecturers. The program is held in English, so you can feel yourself a really international student. We have a tradition that our students have a lot of chances to try themselves as a researcher, as a designer, maybe do something by your own hands. So a lot of chances are for you. The program is internationally recognized. You can see here a certificate. We did not make some prolongation due to some specific reasons, but nevertheless, the program is accredited. It is maybe the very time to think about admission. If you want to study in Samara University, to study GNSS technology, you can try at least look at the site of our university, website. It is just a page of this site where you can know more about admission politics and procedure and so on. Now, I think that I was not too tiresome. You maybe have known something useful, and I am glad that my lecture was interesting for you. So, I hope to see you in the university. Hasta pronto.
Estimados amigos, ahorita está con nosotros el profesor Ilya Alexeyevich Kudryavtsev, investigador senior de la Universidad Aeroespacial de Samara. Podrá contestar directamente sus preguntas, las pueden hacer en vivo o escribir en el chat.
Excelente, muchas gracias a nuestro expositor, a Илья Алексеевич. Илья Алексеевич, мы вам очень благодарны за лекцию. Вот, и вот тут пишут большое спасибо за такую конференцию. ¿Nadie tiene ninguna pregunta, ningún comentario que quieren ahorita decirnos? Павел, у нас есть комментарий.
Thank you for your question. Do you hear me?
Yeah, we hear you.
Okay. The difference is specific. The GPS is the first system belonging to the United States. GLONASS is maybe the second, is more or less the same. The idea of all the systems is more or less similar. However, some opportunities provided by these systems could be different. For example, Galileo is now just in stage of evolving. We hope that it will provide more services than GPS and GLONASS do at the moment. I cannot say much about Baidu, China. You know that it is just on its third stage of evolving from 2020. At the moment, they have many satellites, so they are available maybe at any point of the world. However, we have no much information about it. So typically all the systems are systems for positioning, and you can combine several systems to see more satellites, to get more information about your position, about to say the signals and so on. However, details of the difference could be very sophisticated. Different signals, different bandwidths, different methods of coding, and so on. Maybe this is enough.
Muchas gracias. ¿Alguna otra pregunta, estimados asistentes? Bueno, si no hay, entonces agradecemos, no, sí. Entonces agradecemos a Ilya Alexeyevich por la presentación, por la conferencia y por las respuestas. Y también agradecemos a todos por asistir a la conferencia. Nos vemos en la siguiente conferencia a la 1 de la tarde, hora Ciudad de México. Pavel, tu palabra.
Sí, gracias, estimados participantes. En la 1 de la tarde a México, veremos un vídeo sobre una de las principales universidades de Rusia, el Escuela Superior de Economía. Y después de esto descansamos y tenemos una otra conferencia en el tema Introducción a la teoría del riesgo, explorando la probabilidad de ruina, estrategias de reaseguro y distribución de dividendos, por doctorado Arnold Morena Franco. Gracias, colegas. Tendremos la conferencia en la 1 a la 1 de la tarde. А
Илья
México.
Алексеевич, большое вам спасибо за подключение и за интересную конференцию.
Спасибо вам за эту возможность.
Всего хорошего, до встречи.
До свидания.
Hasta pronto.
Gracias a todos por su presencia, colegas.